This is video 6 of Computer Science 2124. We just discussed at some length the insert operation, and I did some hand waving in that. You let me get away with, oh, the cursor could be pointing here, oh, the cursor could be pointing there. But at the moment, we don't have any way to position the cursor anywhere. Why? Because that original wish list of things we want our linked list to be able to do, it really was not aware that there was such a thing as a cursor to serve as a bookmark or to hang on to a current position or whatever. So now we've got to go back and revise our ADT wish list of operations so that we can move the cursor. Operations to move cursor. Why? Because sometimes we want to put a note at the beginning of the list. Sometimes we want to put a note at the end of the list. Sometimes we want it to go in the middle of the list. Yada, yada, yada. So I'm going to suggest that we can probably get away with these. I think we're up to number 6. Move the cursor to next node. I know that's illegible. I'm sorry. Move the cursor to next node. 7. Well, let's ponder this for just a second. That's a one-way trip. Cursor equals cursor next is going to take us one at a time down through the list. But once we get down there, there's no way to come back. So we're going to probably want a move to front, camel case. And I don't even have to describe that. Isn't that self-explanatory? We move the cursor to the front of the list. Oh, okay, I'll put it up here. Move cursor to front of the list. Hold still. Now then, so now we can come back to the beginning and go through all the way through that again. Ponder again. I'll go ahead and put the number up here. Yeah, there's going to be another one. If we are using this to implement our unbounded case of an unbounded buffer, in other words, a queue, it's called a queue, it's the British word for line. They don't stand in lines, they stand in queues. So if we're going to use this to implement a queue, we're going to be taking things off the front of our list and putting things on the back of our list. So it's going to be very handy rather than having to call move in a loop. Move, 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 move. We could just say go to the back. Move to back. And I'm going to get away with ditto mark. So ditto, 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 ditto to back of list. Move the cursor to the back of the list. Now, these those have to be mutators, of course, because cursor is a state variable, a private variable. So those are definitely going to change the state of the list. We should be able, famous last words, we should be able to knock these out without too much pain and suffering. I hope. 6, the move operation. Almost a trivial before and after picture. Here's before. I'll just jump into the general case. Before the cursor, C for cursor, points at A, maybe. I put that to say it might be an arbitrary position in the list. It might not be the first or the last or whatever. And we'll go from A to Z, just like that arrow on the Amazon trucks. Oh no, what should my after picture look like? Well, duh. After, it takes longer to draw the picture than it would to actually write the code. But that's the price we pay for being deliberate. There you go. Before and after. Before, messy little black cloud there. Before, a cursor points at a node in the list. After, it points at the next node in the list. The picture takes a lot longer to write than the code. Set cursor to cursor arrow next. Right? Here's cursor. Cursor points here. The right-hand side, what is cursor arrow next? Cursor arrow next is the address in this case of node Z. So I'm taking the address of node Z and assigning that to be the new cursor value. So C now holds the address of node Z. Done, 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 and done. But that's the general case. Those pesky boundary conditions, will they get you every time? What if the cursor points at the very beginning of the list, the empty head node? That's possible. Well, this should still work. It should still work in the general case, right? If our list is not empty, oh, that's a special case. If the list is empty and the cursor is pointing at the empty head node, we don't want it to jump off the ledge. We don't want the cursor to be set to 0. That would violate our deeply held class invariant there. So we got to be careful. Now, the empty list is actually a special case of another boundary condition. What if Z is not just another face in the crowd? What if it is the absolute last node in the list? I'm setting you up here. There, absolute last node in the list. And our main program is trying to move somewhere. And they call move, and then they call move again. We don't want them to move again here. They can't do that. So somehow or another, we've got to detect whether or not it's even possible to move the cursor without violating a class invariant. We are not going to set cursor to 0 and go back to the main program. We're going to observe our own self-imposed rules, also known as class invariants. So we better check. We do this conditionally. If, now, here's a couple things. If we can't do it, let's get out of here. If cursor arrow next is 0. There's a condition. If cursor arrow next is 0, we can't do it. Can't move. Can't move. It'll go off the end of the list. And the convention is, if it's possible we're not going to be able to do the job that the main program wants us to do, let's get out of here immediately. Return false. If cursor arrow next is 0, return false. In other words, if there's some way to detect right at the very beginning of a function that we're not going to be able to complete that activity, then get the heck out of Dodge. Return false and forget about it. This then, I'm sorry I indented, this becomes an implicit else. And if you remember what that was, that means if we're still here, then it will do this. So if the cursor arrow next to 0, we can't complete the operation, we're gone. If we're still here, that means the cursor arrow next is not 0, and by yet another convention, any pointer that we leave not 0, we're going to assume by convention that points at something valid. It's not a garbage pointer, it's a legitimate pointer. And if all the other functions up to this point, the insert and the constructor and everybody have been playing by the rules, then if cursor arrow next is not 0, it points to a node that we can move to. See how complicated these things get? They're all their little lives are intertwined, and one of them affects all the others. Set cursor to cursor arrow next, and if we're able to do that, the cursor is moved, everybody's happy, and we need to let the main program know about it. Return true. There you have it, a move operation. Now you might wonder, I'll wonder for you, since you can't talk to me, you might wonder why this convention of checking to see if there's no work that can be done and immediately get out. If we get as far in this semester as my greatest hopes and dreams, then we might even look at some recursive functions. And recursion is always designed so that you test for base cases first. You test for the case that, you know what, I've hit rock bottom, I don't want to go any further, let's go back. Here's hitting rock bottom, I'm at the very end of the list. Even if the list is empty, this condition still works. If I'm at rock bottom, I go back. Otherwise, I do some work and eventually return true. Okay? Slip that little thing in there. We'll see. That's for future reference. Okay, are there any questions about the move operation before I erase it? Okay, here it goes. 7. Move to front. Everybody gets their own before and after picture. All functions created equal. Head points at the empty head node. You better. And node M, way out here in the middle somewhere. Who knows where it is? Maybe it's the last node, maybe it's the middle node. M for middle. Maybe that's where the cursor points. This is my before picture, by the way. After. Head, cursor. There's still the empty head node. The head pointer still points at the empty head node. Everybody's got to play by the rules. Node M, certainly not going to make it go away. It's not going to put any new node in there. Node M is still there. Well, that's different. Well, at the moment, the cursor doesn't point at anything. Move to front should point the cursor to the empty head node. Are we sure? Maybe we should point the cursor to the second node, because that's the first one that's got any data in it. No, we want the cursor to point at the empty head node, because the whole reason of calling move to front might be that we want to put a new first real node in the list. Notice I call it the first real node. The first node will always be this placeholder, garbage empty head node, but the first real node, we want to be able to put another first real node in the list, depending on the application. So no, we don't want the cursor to point at head arrow next. We want it to point at the head empty head node. So that now, think about this real hard. If we go back to the previous video and now call insert, then the new node that's inserted will be squeezed between the empty head node and the old first real node. Man, I'm getting in a terminology hole dug for myself here. But cursor, yeah. Bottom line is we want cursor to point to the empty head node. How do we do that? We set cursor to head arrow next. No, I just now said no. Set cursor to head. Step 1. Step 2, closing curly bracket. There's nothing to do. We don't even return true or false. Why not? How do we always know we'll be able to set cursor to head and not be violating class invariance and just now set the cursor to 0 or whatever? Oh, well, by the courtesy of our class invariance, we know it's always possible to do this without setting the cursor to 0 because our class invariance said head pointer always has to point the empty head node. And the empty head node does not live at address 0. Nobody does. So setting cursor to head doesn't cause any problems. This is a one-step algorithm. It took a lot longer to get the setup for it than it did to actually write the code. But you still want to do that. You still want to look at the before and after picture and consider, what are the special cases? Do I need to be careful about this? Do I need to be careful about that? You don't want to just get in the habit of saying, well, you know what? I think I'll just knock this out as a couple of lines. I'll just write down the lines and be done. Don't do that. Okay, we're done with number 7. Knocking these out in a hurry. Number 8, move to back. Before, head, cursor, garbage head node, yada, 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 cursor points to node, N, and yada, yada, yada. What letter have I not used? Q. Q is the last node of the list. Now, before I even do the after picture of this, let's talk about this abstractly. Of course, I will draw the pictures, just in my nature, I'll have to. But we want the cursor, when all the smoke clears, to be pointing at node Q. And we have the machinery in place, if we've implemented the code up to this point, to do that. Look what we could do. Think about this real hard. We could call move, regardless where the cursor is. It could already be pointing at the last, it could be pointing at the front, be pointing at the middle where it is. We could call move, 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 until it returns false. while move returns true, keep going and inchworm your way down through the list. Do you see how that would work? As long as it's possible to move, that means that there is a next node to move to, and our move function is returning true or false to say whether or not it was successful. When the cursor finally points at node Q, then when we call move, it's going to return false. No, I can't move any further. In which case, the cursor will be pointed at the last node. What could be simpler? Well, we're not going to do that. These letters, little nodes on the board, they deceive you. There's actually 3 million nodes between N and Q. We've already talked a little bit about order of magnitude operation, right? That's order N, meaning if there are twice as many nodes as there were before, it's going to take the cursor twice as long to move to the end. If I go from how many nodes there are now, and now there's 1,000,000 times more nodes from where the cursor is to the end, it's going to take 1,000,000 times more for it to execute. 1,000,000 times as long. 1,000,000 times as many instructions. So that's going to be a problem. It's not a problem to implement. It's a problem in that it's inefficient. Why do we care? Because think about this again. Here come those big blue madness tickets, which unfortunately, we might not be able to buy those for a while. But if this is used to implement a queue, British line, then we're going to be taking things from the front of the list over here and putting things in the back. And we're going to be using the cursor for both those operations. If we put things in the back, the cursor's got to move all the way to the end before we're ready to insert anything. And then we got to turn around when we're ready to get somebody off the front of the line. We come over here to the first real node in the list and take that one. So the cursor's going to have to move up there. We haven't looked at the remove operation yet, but we will. Chicken and egg problem again. If the cursor points at this, then that, then this, then that, and every time we have to flip back and forth, the cursor has to go move, possibly millions of times, then that's going to take a long time, and it's very inefficient, and it's bad. Ugh. No move in a loop. What does that violate? That violates keeping the common case fast. The common case, if this list is being used to implement a queue, the common case is that we are going to have to zip the cursor back and forth, maybe not every single operation, get a few off the front, insert a few in the back, but still, every time we move from front to back, we've got to go through all the other nodes in between. Oh, woe is us. That's order in, script O in. Twice the length of the list, twice as long for the operation. 10 times the length of the list, 10 times longer for the operation. Woe is us. What could we possibly do? Well, we'll have to wait till video 7 to find out. We can turn this into an order 1 operation. In other words, it takes exactly the same amount of time, regardless of how long the list is. But there's a price to pay. See you online.